Okay, so let me start again. Welcome everyone to the afternoon session. We're going to start the session with a keynote by Ramón Medrano. He's a site reliability engineer at Google. He's leading the identity team and is responsible for keeping the bar of the quality for Google products up and very high. Yes. Before working at Google, he worked at CERN, and now he's also working on his PhD in autonomic system management.
That's correct. Thank you.
Ramón.
Thank you. So, good afternoon, everyone. So, do you have a Google account? That's what my team does that. So, I manage a team of we're 25 people that we manage all the authentication service. So, from your accounts.google.com login page to the storage of the passwords and usernames, settings, stuff like that. So, we manage a few tens of services. We are in the since a few years actually we are going through a transformation from having like the 3 layers monolith, where we had a service that was called front end, another that was called back end, and another that was called storage. Those are real names. And then we are moving towards microservices. We are more or less done with the front end part. So in the front end, we're in the brave new world of running 60 services for doing the same thing. Well, there is increased scope, but it's the serving basically the login page, OAuth, grants, and your settings for your account, right? And in the backend, which is like a major service, so we still are running a monolith service with like a millions lines of code in C++, which is replicated in like more than 20 clusters worldwide, right? And it runs things from like creating accounts towards, for example, when you provide us with your username and password, issuing you with a cookie that then you're going to come back to us to validate, right? Those are very critical services, basically because if we can't validate your cookies, for example, no Google property can operate. Like if you well, maybe search probably operates without you being logged in your account, but otherwise, if you want to check in your Gmail and our cookie validation service, for example, is down, and you give us a cookie that we can't validate, you can't access your email or your Google Drive or blah, 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 all the other sites, right? So we are transforming the backend service into microservices, basically for maintainability. So it's a chunk of code that is serving for multiple functionality, from OAuth stuff to like cookies to password verification, right? And it's been an interesting journey. So while I was preparing the presentation, I just realized that I didn't wrote the growth microservice in the whole slide set. So the things that the reliability, as we see it, it goes for monoliths to microservices to whatever you're doing. It depends on your problem that you're trying to solve, right? It's true that running microservices will allow you to do certain things that with monoliths they are more difficult, especially at scale. For example, running a big amount of replicas of a monolith is usually more complicated than with microservices, right? Because the code and this functionality in a microservice is way more scoped for what you have to do. In a monolith, it's very easy to add a state here and there. Like, for example, caches, in-process caches, like files in your file system that you are running, and so on, right? But in general, the traits for reliability is the same whether you run 60 different microservices or just one monolith, right? So that's what I'm going to cover in the presentation today, right? So we go from an introduction to SRE, right, in 5 minutes, and then how we go to ensure reliability from the hardware reliability, which TLDR, there is no reliability in hardware, is going to fail, right? So you need to design your software so you can actually overcome hardware that is always failing, right? And then what you do, for example, for cases, so how you do to prevent like failure by designing your system for reliability, and how you tolerate failures, right? How you run your service in a degrade state. I know that my services are in a degrade state right now, all the time, right? So you have to take that into account from the design and development phase, right? So I think I was happy to have this presentation in the development day, because I think reliability is more of a designer development than any other phase of the lifetime of a service. So first of all, what is SRE? So site is basically a historical word in there. When there was only google.com, there was the site, right? Now we have teams that they do sites like mail.google.com, or they have internal infrastructure like our releases and rollouts services, or our master election software, for example, right? Which is not technically a site. So we guarantee, or we work in three things, right? The first one is the availability and reliability, right? So when our services, in the case of, for example, accounts.google.com, which is where you put your user password, is available all the time as we want, and is reliable, meaning that it's not only available, but it's doing the right thing. Like a case of availability of accounts.google.com that is not reliable is very easy. It's like we can show you the login form, right? But we will issue you a cookie, whatever you put in there, right? That's a service is available, but it's totally not reliable because we are logging in anyone in the world to any account that you choose, right? That's not what we want. And then when those properties are fulfilled to a service level that we determine for the criticality of the service for our business, which is never 100%, then we work in maintainability. So maintainability means that we are gonna make the service basically cheaper to run and easier to upgrade and easy to change, right? For example, we're gonna invest in automation to do our rollouts, or we are gonna invest in monitoring to be able to have more insights of the service and how we can optimize it, and so on and so forth, right? In the case of the SRE, since the beginning, because we have plenty of services, but towards the movement of microservice, there is a steep learning curve. So when you are a noodler that we hire and you put them in my team, right, there you go. Here are 65 services that they are all interconnected to do something. Like for example, changing your preference for the ads personalization, which is storing a byte in one database, right? That's what they do. You need 60 of those. And then many of the teams, what we have done is as well, specialize them. So there is not a SRE team at Google. So we have an SRE organization, but there are plenty of SRE teams that they focus in very specific parts of infrastructure or actual products, right? For example, there is a Gmail SRE team, and there is an identity SRE team. They are like more or less products that they are very identifiable by users, but we have plenty of SRE teams that they are focusing in infrastructure. Like our monitoring consoles, there is a team for that. There is for releases and rollouts for the staff, there is a team for that. For our master election software and Chavi file system, for example, there is a team for that, etc. So availability and maintainability, right? These are the two easy parts of the three things that we do, right? Availability is rather easy to understand, right? It's like how much or how proportion of the time your software was available for your customers. We do have SLAs, for example, in G Suite, there is a 3 nines SLA, so 99.9%, right? And we typically exceed that. Like the SLAs that we determine, we typically exceed those. When we don't meet our SLAs, for example, if you use Google Cloud Platform, you can get a discount for your next usage or whatever. So there is some kind of agreement with the customers of what that means, violating the SLA, right? And then maintainability, right? And just availability, for example, as well is easy to obtain, right? It's not that difficult these days to achieve like these high levels of availability. If you run, for example, replicated stateless software in any cloud provider of your choosing, there you go. It's like it's not that. I mean, it's difficult, but it's okay. It's doable, right? But even by a small team of developers, maintainability as well. Like for example, we do not have like windows of updates, so we design our services to be updated and rolled out and changed all the time. For example, our front-end services, they would do like one pre-release every day and a couple of production releases every week. Backend servers too. The storage, for example, this is a service that is a bit more old. They would do one release every other week, something like that. They are in a phase that they need less feature development, for example, right? But there is no like a window, like for example in my bank, all the time they say like on Sunday 15 between 2 a.m. and 4 a.m. you will not be able to access your service. We don't do that, right? On the other hand, maintainability is more than how to change your system, it's as well how you debug it. Like how when you have an outage on your page, for example, that users can't log in. Well, you are very much screwed if you are on call at that date, but maintainability means as well the tooling that you have to debug these issues. So your medium time to repair, for example, is shorter than if you will not have all those toolings, right? Especially with microservices, there is a change of paradigm of how you debug things. If you have a monolith, you just attach GDB to that thing, and you start seeing the stack trace, and everything is good. With microservices, you start to debug a service mesh, for example. So you have to start tracing RPCs, where are they going, and where are they being failed, and what is the return code, and why are they failing in this binary that I really don't know what is doing, right? And reliability. So the reliability is a very interesting concept, right? Because reliability is something that you can rely, something is reliable when you can rely on it to put your data, etc. So we do study the reliability of everything in our network. I think Google is the largest network in the world right now, right? So we build our own machines and blah, 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 our own data centers, etc. But there is a study of reliability of every single component in that network. For example, we know what is the lifetime of a building that hosts the computers. We know for in each of the data centers that they have several clusters, for example, we know how long they can live, right? What is the profile that they have for failures. We know in each of the racks, for example, of the machines that we have in the data centers, what is the lifetime of those, right? So the reliability, you need to study of each of the components that you are gonna be using. You need to understand it, and you need to as well to be able to use them for a mission that is what you want, right? So let me say how I put this. So for example, if you want to run a service that is intensive in compute, right? You might want to use computers that they have, for example, with the new cloud thing, you might want to use for your machine learning stuff, which is very intensive in computing, you might want to use specific hardware for that purpose. If you're running Gmail, for example, and you don't need that, you might want to use other computers that they are simpler and therefore probably more reliable, right? The simpler, generally more reliable. All the services we have, all the systems we have, they are redundant by design. So all the machines, they have, like for example, 2 PSUs in the machine. All the machines, all the racks, they have several machines. All the services we do have, they are replicated in different copies of the same cluster. All the clusters, they are replicated along the different data centers. Data centers are replicated too, and blah, blah, blah. There is one thing that is not replicated, that is the service itself, the system. The google.com where you search, there is only one, right? That's the only thing that you can't replicate, sadly, right? But we have all the whole 9 yards of replications. Like for example, we have data which is copied across different machines in different data centers and so on, right? We do this redundancy from the beginning. Like when we are designing a system, for example, we are going to launch Gmail, the new front end of Gmail, for example, that launched a few months ago. So there was a design process and then an implementation process. So all the reliability analysis was done at the beginning. It's like, okay, how much do you want this service to be reliable? And then you define an SLO as your service level objective. It's like, this service is very important for the company because of revenue, blah, 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 and has to be 4 nines. That is 99.99%, 4 nines, right? So there you go. With that assumptions, then you design the systems in another way or in another. If it's a system that is not that critical, you might choose not to make it that redundant, right? If it's a system that is really, really critical, for example, the cookie validation server is replicated 3 ways in all 20 data centers that we have, because it's super important to have that database up and running, right? So there you have 60 copies of the thing, and so on. So, one thing we need to assume when designing a service, be it a computing service or a system in generic terms, right, is that hardware is going to fail all the time, right? When you have a single machine, it will have a lifetime profile, right? So you will have something like this. So if you have like a the time and the probability of failure is going to be something like this. I'm sure many of those here know this. This is the bathtub curve, right? So if at the beginning the machines can fail because they are poorly manufactured. Okay, if we remove those machines, then they are fine from the time, and then they start failing. When you have one, that's fine. It's going to last you for a few years. That's okay, right? When you have 50 millions of these, or 15,000, or X, being X bigger than 100, you know that one of those is going to be failing for sure, all the time, right? So you need to design your systems taking into account these things. And this curve will apply to any of your machines, but any of your components too. Your power supplies units, the diesel engines that you have in your data center for when the power goes out. You'll have your processors, for example, your memory sticks. You'll have your racks. They will have different profile, but there is one model that you can use for each of your components to determine what is the lifetime and what is the aging process that is taking, right? With that, we do apply best practices, for example, to determine how long we can keep machines in the fleet. How many replicas do we have to have per component? Is enough? I mean, is enough? One question is like, is enough to have one diesel generator in a data center, or should we have two? Then you will need to understand the reliability of your component and determine what you need from it for the mission that is giving you, right? For example, if you want to have I don't know, 5 nines of availability of each of the data centers, and in Belgium, that is what we have, one big data centers, the utility, for example, is very reliable. You say like, okay, fine, with one it's going to be okay, right? Because the probability of having the thing broken plus the utility down might not be that high, or might be tolerable for what you want. Or if you run in another utility, for example, that is not that good, you might want to have 2, depending on how you model your stuff, right? This is important for reporting as well the service life of your components. So you might want to see like when do I have to replace these computers and so on, for budgetary things, for planning, for manufacturing. When you buy computers in the cloud provider, for example, a GCP or AWS or whatever, is very easy because you go, you click, and you get it. When you build your own data centers, you might need 3 years of building the actual concrete envelope that the computers are in, right? So as well, one thing that changes over time is the requirements you have, right? When you build your machines for doing your machine learning, you say like, okay, I'm doing a few things in machine learning, for example. I think like I might buy these machines with a GPU, and that's okay. That's okay today, right? Then this machine is going to last you like 3-4 years, for example. You invested like several thousand euros in those machines, right? And then you say like, well, how come is that possible that now I rely a lot in machine learning and my machines are not able to like supply me with the capacity I need, right? So it's typically something that we understand, like if you make a decision with data that was 1 year old, that decision is going to be wrong, right? So we need to re-estimate all these models all the time. So what we do for that is just we use real-time data from the machines that we have in our fleet. So whenever they die, a disk died, for example, you just, okay, throw it away, and then you record which is the serial number, what is the generation, what was the capacity, what was the vendor, what was the why it just broke, right? And then all these models are dynamically adapting over time. So whenever you need to do decisions over like what is the lifetime of machines, how you wanna replicate your service, you always have data that is fresh as of today, right? You obviously can do that when you have certain scale, but yes, it's what it is. So you might say like the customer changes, right? And then you have an envelope that you have in what I call the envelope, that is the environment basically, which is how is your service running, right? It's like how much, for example, if we speak about software, it's like how much effort are you putting in what we call toil, that is operations. Like for example, when doing releases, you have to do them by hand. That's totally fine, doing releases by hand. I mean, depends on what is the mission that you have with that system, right? If it's a system that you release once a month, that's okay. You might not see any return of investment by automating that. because it's okay. You might just have to do it by hand. That's fine. If on the opposite, you have a system, for example, that you want to release with a lot of cadence because it's a system that is critical for the future of your business, and then you want to do a release per day, then you might want to actually invest in changing how you do your releases, right? So the envelope you have, that is what you have right now, and the mission that you want to fulfill with your software, with your system, with your machine, that changes over time. And then you need to reassess how you do your things. Being like how many machines, which type of machines, or for things like should you use a service mesh or not, right? All of these are the same questions. Like there's a trade-off between like the cost it has for maintaining and doing it, and the need or the benefit you get from it. So you can think of it as, for example, something that is probably easier to understand is an aircraft. So you want to have an aircraft, right? There are three options that you have. You can buy your own, which is not many people can do it, but let's assume that you can go buy your own aircraft, right? A nice Cessna there. And then you can rent it. And there are two rental agencies for you. There's one that charges by the time you're using, the time you're flying, and another one that charges by how much engine you are using, how much crankshaft revolutions you are using, right? So depends what you are going to do, what you intend to do, what you intend to do. You might need to consider the three options, right? If you're going to be flying all the time, well, maybe buying your own is not that bad. You need to understand that there are many metrics that you need to take into account besides the cost of the aircraft. There is a pilot. There are times that the aircraft is going to be landed because it has to be in revisions and they have to change blah, and you can't use it. You might need to get the second one, right? There is the depending how is your profile of traveling, you might need to use one kind of rental or another. So if you say like, I really need to travel fast, right? Then the option is clear, right? Then if you travel like, I don't care about the time, I just want to travel, maybe the other option, the touch, is cheaper. But that has different impact in how your aircraft is going to age, right? So if you run with the first rental option, what you really want is to run to fly very fast, so you shorten the time you're using the machine, right? That will put stress in the engines. So that part, that component, is going to be stressing and aging very fast. What you're going to see is that this curve is going to look more like this, right? If you, for the opposite, you don't care about the time that you take to go to the places, you might choose the other option. But the other option is going to run a colder engine, but it's going to put more stress in the airframe, for example. So the other component, while the engine, you may see an effect of like a longer lifetime, you may see other components that they stress in a different fashion, right? So depending how you compose your components to create the system, you are going to have a different pattern on how they break, right? For example, in computing it's very easy. If you are I'm running machine learning in a GPU, right? That's going to put a lot of heat in your case, right? That might affect things like your disks. If you're just running a web server, for example, that is just serving things from a cache, that machine is probably going to run colder, right? So the disks, they might last longer than in the machine that is running hotter. Those are trade-offs that you need to understand when you are designing for reliability, and they are going to change the models of the lifetime of your components and services, right? So redundant services, right? If you have any questions, just make such a question. We are going to do them at the end, but why not, right? So the redundancy is very nice, right? Is the panacea of fixing reliability of systems. Maybe. That's like everyone says, it depends. So when you have components that they are redundant, you have more likelihood of failing, right? So you need to be more aware of failure when you have components that they are redundant. If you have a system that is like this, right? Let's say the typical, you have your front end, your back end, and the storage, right? Boom. That's the classical 3 layers thing that is gonna, you have 3 monoliths that is gonna surprisingly last you forever. Like you can really go further with this thing. We went 15 years with high scale, and it's good, right? Then there is a moment that okay, fine, you need to design for reliability, and you want to say like, okay, the backend, I'm gonna replicate my backend, right? So now you have something like this, right? Then there is there are several problems that you have when you have this stuff. First of all, before we look at the slide, can you do that? There are many cases that you can't do that because the backend has a state, right? So there you go. You need to put your cache. The cache that the backend had in process, you need to put it out, right? And then you can replicate it. But then, what happens if there is what we call share fate? So if there is a query, for example, that crashes your backend. So you send a query through an RPC endpoint, and it just sexfolds these things. So you start sending the queries, and the things start dying. Congratulations, you have a replicated failure now, but the thing is down. Right? When you have a system like this will have a medium time to fail, right? If you have one, that's well understood. When you have several, let's think, for example, the engines of a plane. Like when you have an A330, for example, with 2 engines, they do have a very understandable medium time to fail for the engines. If you say, like, I want to make it more reliable by adding 2 more engines, yes, you are going to increase the proportion of time that the plane has at least 1 engine running, right? But the probability of having 1 engine failing is higher, right? So you might have higher availability of the thrust for the plane, but you might have more cases of the plane going into maintenance because one of the engines is broken, right? Then you have another critical subsystem, right? In these cases, that is in here, for example, from the backend to the storage. The storage is something that is stateful, so you might not be able to do that, and you might need to put here like a load balancer. Right? Then, okay, you replicated all your backend, which is very good. Now you have replicated backend, but you now have another single point of failure. The load balancing that this is hypothetical, right? But it's typical that in the storage, for example, which is stateless, there is some idiosyncrasies there, right? So you need to add like a collector of entries, right? There you have another single point of failure. It's true that it's usually more simpler, and simpler means more reliable and easy to repair, right? So in this case, this system might be better than before because this thing, even though it's a single point of failure, is easier to repair and easy to understand, right? More reliable, but that's something you need to understand. So what happens as well in degrade mode? So I think it's an interesting concept, especially for microservices, that we need to understand. That is, so imagine that you have that front end, and you go the whole 9 yards of like you're gonna do a service mesh. So you want to present one page to the user, right? So you want to present one page to the user that is composed of 3 informations that you want to show, like is your name, your birthday, and your email. And you go like how one does, that is a single binary for representing each of the information. So this is very self-contained and easy to deploy, right? So this is the name, which is very loaded, so you have many replicas, right? And this is the birthday, which is less loaded, right? So the point is like, what happens if your email showing services is down, right? This thing is down because of reason foo, right? What you do in there, like you just fail, the backend fails, all the requests is like, user, we can't show you the page, come back later, right? Or you operate in a degraded mode, meaning like the page is going to show your name and your birthday, but it's not going to show your email because that backend is down, right? That's something that microservices do enable in an easier way than a monolith, right? Because you can send all your RPCs and just compose the page conditionally, for example, with the responses that you are getting. In a monolith, you can do it too, right? But for my experience, what I have seen is that the code tends to be a bit more crafty for supporting this stuff, right? As well, another thing that they enable is, for example, the scalability is going to be of all these microservices is going to be independent, right? But you all know that. And then operations, they become different, right? So when you have an architecture like this, right, you start seeing that they are like systems that they might be critical or single point of failure for the total of the systems, right? So how you do rollout, for example, with your monoliths is something that is probably very understood. So you have a new version of the binary, you do a progressive rollout to 10% of your replicas, for example. You say, like, okay, serving well. during an hour, and then I go, right? When you do rollouts for all of these, you may need to have an orchestrator just for the rollouts, because you might want to say like, okay, I'm gonna roll out backend 3, but there is a rollout of the cache as well going, which this cache is at half capacity because being rollout, these things start polluting the cache, and this affects the backend 1, which doesn't have fresh data, and therefore the latency is way higher than it used to be, right? Boom, your operations change. So, how to address this? A few things. Like you need to assume that the risk of failing components is the same. They're all share fate unless you can prove that they are otherwise. Like if you are having microservices, you need to assume that all of them can fail at the same time, which is not the difference from your monolith, though, unless you can prove that they can't fail with different profiles. If you can prove that, then you have increased your availability, right? Obviously, if you have 15,000 replicas of a microservice, for example, that is mutating a database, you have 15,000 more probabilities of corrupting that database than if you're running one, right? Additional systems, for example, this load balancer that we put to support the backends in a replicated fashion to access storage, need to be simpler, right? Need to be simpler because otherwise you are just adding complexity because you can. Catastrophic situations should be avoided, especially when you are running a service in a normal planning. So when you are planning how to do operations and so on, you should think what are the possible cascading failures, for example, as we call it. That is, one component failure in that architecture might trigger failures in the whole mesh of services that you have. Right? And one thing that is very important I want to remark is that you need to understand that your service, especially when you move to microservices and having more components and network and meshes and all that stuff, is going to operate a lot of the time in degraded mode. Right? So for example, in here, we added like a few services just for redundancy. You need to consider as well that they might be a ways to increase your reliability that is not adding redundant services. That is, for example, simplifying services, right? Simplifying your code base, using the machine type that is more appropriate for what you're doing, right? Hosting your data in another cloud provider. Like, there are many questions for that, right? Here, what is said there, like an output selector with an input selector, is basically this thing, right? So, I mean, imagine that you have two services, then you have like the different multiplexers, right? API gateway, if you're like modern, right? So whenever you these replicas go to the other one, for example, they will just multiplex to the services as well. You can combine these two and make them redundant as well. But you might have a system that does not have any single piece that is not redundant at the end of the day, right? Except for the system itself, maybe, right? So each of the components that you do replicate, they become way more complex, especially if you want to orchestrate them. Like, for example, if you use things like master election, that becomes really, really subtle. Like if you have storage that is replicated, for example, you might want to have a master election in there. It's a very common pattern. Like you have replicated this machine, and each of your replicas needs to have a master, right? Having this is very common as well in microservices, for example, is having the storage replicated in some way. Like either you have a MySQL database with a master slave, for example, or you have replicated state machines like Cassandra and stuff like that, right? The thing is that single piece of code that is your consensus algorithm might be something that you want to replicate too, right? Or might be something that you want to operate and you want to upgrade to. For example, at Google, we use Paxos very often for many of our databases, right? And it's a system that is, well, I mean, they explain you and it looks fine until you try to read it, right? It's like, holy, like, it's complex, let's say, right? And then the thing is that you start building databases with that, and then you start operating the system, and then you start understanding and patching, and you have a system that is more or less reliable, right? And then you want to say, like, so I want to increase my reliability by having a system that is easier for understanding, something that is more intuitive, right? For example, there is Raft. Raft is another consensus algorithm. Like if you use etcd, for example, that uses Raft. It's in the core of Kubernetes, if you use Kubernetes, right? So you want to say, I want to change all my Paxos implementations by Raft because it's going to make me more reliable because it's simpler to understand, right? Okay, fine. You need to prove to me that Raft is going to be able to cover all the use cases that Paxos is going. And if you, like someone was presenting before, if you have a culture of copy pasting, those can be difficult. Or if you have culture like we have of like having a single repo and everyone including one of our libraries for Paxos, that can be difficult too, because you don't know what are all the context that that library is being used into, right? So what you get into, like even replacing software components that they seem very replaceable is not going to be easy. And it's a trade-off of like how much are you going to invest for that and what is the diff that you are going to get in availability, for example, by changing one of the libraries, right? We do have an entire team, software developers team, dedicated to that Paxos library and an SRE team dedicated to the Paxos library because it's a core piece of infrastructure, right? So for computer systems, like I'm just close to be done for the question. So hardware and architectural redundancy is good, like in non-computing systems, like in everything. You are going to have redundancy in all over the places, from the functional units to the processor, to the cache lines of the processor, the registry file, then you have to the memory, you have now redundant buses, then you have like a memory with error correction, that's like information redundancy, then you are going to have different copies of the information, then you are going to have the machines in your racks with two network interface cards, then you're going to have two top of the switch racks because why not, they're cheap, then you're going to have two data centers that you might want to have as well a cloud provider you can offload your data to in case the thing breaks. So redundancy, I think hardware redundancy is very easy. Architecture redundancy is that, it's just copy your software many times. You need to design your software though that so can be replicated, which is usually is easy until it stops being easy. In storage, it's very tricky to make it right without data corruption, I guess. The information redundancy is from error codes to having different copies of the information, having backups, data integrity, for example. You only have backups when you have a backup and you restore it, by the way. So that's part of the information redundancy. And time redundancy. Time redundancy is something that is easy to understand, that is doing retries. Like, for example, you send an RPC for your front end to your back end, it does fail. Okay, let me send it again. It succeeds. Okay, fine. Redundancy in time, right? You can do that unless you can't. For example, you send an RPC from the backend to the storage. It does for a mutation, for example, to mutate the password of a user foo, right? So you send the RPC for the mutation, and you don't get any answer, right? How you do that, right? So in those cases, for example, you can use like the read, update, mutate, which is you read your data, you mutate, and then you read it again and compare what was the mutation that you were doing. It's read, modify, compare, right? And there are schemas for like how to do it right? But generally retries. We do retries. Every single RPC that we send within Google has like automatic retry. Software redundancy. That was one that is very interesting. Like, for example, that no one is not typically thought of. Like when you write code, you write your code in a file that you can read, right? And then you use a tool, which is a component of your whole infrastructure. It's called a compiler to compile it, right? You can use two compilers. You can use GCC and Clang and compile two different binaries that might fail under different conditions or might incorporate different bugs, right? You need to use all of these things at the same time, or more than one, generally, because one of these techniques, they are going to cover only one failure scenario. Other techniques combined, they might provide you more resiliency, right? If you move to things like microservices, you're going to be tempted to use these kind of things, like the composers, right? If you really want to be reliable, the next step is to use, for example, service mesh, which you remove that thing, but you add other complexities. This is how you distribute the configuration. You need a control plane that might not be redundant, and you can go deeper and deeper and deeper to a rabbit hole forever. So degradation, that's something that's very hard to plan for, because you typically have two systems in one. So when you have your system, like this system, this is a whole system with different components, typically it's going to operate in the normal mode. Or if you have a plane that has two engines, you typically are going to be able to use the thrust in two engines, right? Fine. What happens if is not the case? So you have another specification of the system, right? You have a system that is now this. This is a completely different system that it was before, right? Because the load distribution is going to be different, the functional capabilities are going to be different, the response to the user is going to be different, the stress in different parts of the systems is going to be different, right? So you need to plan to be running with these systems. What have we found as well is that usually if you plan for running in the degrade system, and it's like, well, that's kind of fine, right? Why don't you run always in degrade mode, where you don't remove your components, right? We have removed components because it's like, well, we don't care, right? It's simpler, therefore it's better, right? So you may choose to do that. It's very rare that that happens, though. On the other hand, as you can see in that simple service that you have in there, if you say like, okay, let me do another spec of this system where this is failed too, how does it work? Is it okay or not? You can do all the combinations in there. And it's like, holy shit, this is like a ton of combinations, like exponential basically, right? You might not go down that path of like creating all the combinations of the possibilities for your system, but some scenarios that you understand that can happen more often than others. So the component quality, how you manage that. So this is what we have been discussing all the time. Basically monitoring and understanding your models there, right? So for example, if you have this component, you might, things that we monitor, for example, is the service level indicator. That is like, for example, for this front end, we define an SLI that is how often, for example, what was the proportion of the time that the server was serving the request to the users in less than 100 millisecond latency and with a code of return of 200. So meaning that you need to serve correct responses in less than some time, right? That's an SLI. You might measure, for example, RPCs in, RPCs out, which are the backends that is contacting, and so on. That's how you monitor your systems, right? Systems do age too, like software as well. For example, the code that you have in your front end will have releases. So we'll have people writing code for it, right? It's going to become more complex. It's going to have bugs and so on. So this stuff is going to be degrading all over the time. So you need to monitor that and see how it degrades, right? You have the combinatory that we were discussing, right? And the context of the system is going to be changing all the time, of the component, right? Because the backends, they are being changed as well of the time, and they do have dependencies. That's what I mean. Like, for example, these two components, you might have two backends, but these run in different machines. These machines, for example, that is running this one, might have the AAS functional unit of the processor broken, and the cookies that that backend is issuing are going to be different than the other one. It's the same code, but different context. And the system quality, I mentioned that the system is something that you can't copy, right? You can have two Gmails. We would like to, but generally people want to go to Gmail, not Gmail 1 and Gmail 2, right? So the requirements are changing as well, and there is a point that you can go further. Like 100% availability for our system is not going to be doable, right? In that case, you need to understand what is the trade-off of saying like, I'm making a lot of money with this system, so therefore I want it available all the time. So let's choose 5 nines, right? That's going to completely influence how you compose your components. Then it's like, well, that's a service that we give for free. That's fine. It's going to be 2 nines, right? Then just don't bother with replicating it. Yeah. And then testing. Testing is something that is going to allow you, for example, to validate the assumptions of the invariance of the system all the time. There are testing scenarios that they are, well, more theoretical than not. We have found, for example, load testing a binary does not give you anything. You more or less can estimate how many QPS or queries per second can do, right? But when you put it in production, the context is going to be so different than when you have it in the test bed that the best test that you can do is test in production. Good. So one thing that we do, for example, is the hermetic testing. For example, that's very nice because you can get the same system, right, and run different test scenarios in different virtual machines, right? So what you are testing there is same environment with a different variation, right? So you can isolate whenever your system fails. For example, it's easier to isolate to what was the component that was changed. For example, you can put the whole system in one virtual machine and do a release of a new version of the backend. Does the test pass? Okay. Does the test fail? Well, it has to be that backend that you change, what is broken, what is breaking your service, right? And then you need to continue observing the system. That's very important as well. So each binary release that we do goes through this process of qualification, right? We have monitoring. We can see these metrics that we are gonna taking over each of the components. For example, what is the SLI, what is the front-end latency for some level of load, and so we can compare them, and therefore we can, in this way, we can compare different versions of the same front-end, or whatever is the component that we are releasing, and then say, yes, this can go to production with some confidence or not, right? So, design your software for availability. Don't wait for the thing to be deployed and see how you can make it available. That's not gonna work. You need to understand your components, right? Even if your components is Google Cloud Platform or AWS or whatever, you can understand what is the failure mode of those things, right? Unit tests and regression tests, they are nice, right? If you want to do changes in your system, like that one, it's better to do them serialized if you can. So instead of doing 2 releases at the same time, that will create a cascading failure, just do one by one. There are times that it's so complex that you can't, because you need to do 2, because you have some like releases to go through, some cadence to fulfill, but try. And then monitor. Like observability is key for reliability, especially in services like microservices and service meshes. When you have service mesh that is doing a full mesh, like every service is calling more or less every service, observability is going to be your GDB to debug the things, because you are going to need to trace, for example, where, okay, this request that failed, you need to trace when it ended up going, to which storage replica, to which backend, where was the failure, right? So, well, in SRE, we do like we are developers, we are software engineers, and we are writing the reliability part of the services, let's say, whatever that means. Could be features, could be like a shorter JavaScript. For example, exercise for the reader, like you can calculate how many times per second we issue a new cookie, right? And you can go to your Chrome browser and open one of the multiple cookies that we have. Your main cookie is called seed, and just measure how much bytes does that cookie take, right? And then you can understand what is the difference in our system if we want to increase the cookie size but 1 byte, right? How much more bandwidth and RAM and CPU we might need to incorporate in our system, right? That's something you can think about. And that's it. Any question? We have like 10 minutes.
It's my time to exercise.
Hi, thank you for the talk. I'm interested basically in why do you think your models are correct? Are you like double checking the models? Because it seems that you are taking a lot of important decisions based on the model. So
we do validate the models and we evolve them over time with the data that we collect, like actually from when machines break, when we have like a new release, stuff like that. So it's difficult to say like a formal proof of my model is valid. Empirically, we find them that they are correct when we validate back to what we have.
And do you believe that this model and the accuracy of our predictions are a competitive advantage over other players, or these days are becoming so important, especially if you have a large system, that knowing and having more precise data or monitoring everything is the key to have a competitive advantage over other big companies having big systems?
Yes, without doubt. Like the more precise, if you can observe your system more precisely, you can understand it further, and you can have, it enables you to do anything. From security of like, yes, my network is properly configured, for example, and my ACLs for accessing data are properly configured, so you avoid risks of data exfiltration, shit like that. Then you have things like debugging your system. You can understand your system, therefore you can optimize it to make it cheaper or to add new features or whatever, right? So observability for a microservices, and even not a microservice thing, but when you have a complex structure of binaries running in production, doing RPCs all to each other, right? If you don't have an accurate observability platform for that, you basically can't operate your service reliably.
Thanks for your talk. So you mentioned observability, right? And it came into my mind. Do you know what is the weight of that over your system? I mean, you want to observe something, but that takes bandwidth, storage, CPU, and so on and so forth. So what is the, if you have some measure on that? Thanks.
So we do have measure of the cost of the observability. So I can tell you a few things. I don't know if I can tell this, but for example, in GKE, in the Google Kubernetes engine, I was looking this week about like what is the cost breakdown of like the actual production service and the monitoring they use, and it's a sizable 2 digits percentage, the monitoring one. Another data for you is the priority of the jobs in Borg, that is the orchestrator we run. If you know Kubernetes, it's similar, it's older, like, I mean, it's like was built before. So we have the jobs there are scheduled with some priorities, right? And the bigger priority evicts the older one. The highest priority jobs, they are monitoring jobs all the time. So should we, there is auto-draining. For example, a cluster that has lost the monitoring jobs, we just don't send traffic there, right? Because you can't fly blind, as we say. If you lose your monitoring, you might be operating a system that is doing something bad and you don't know it.
Thank you for your talk. I saw a slide there you were talking about realistic testing with data, and you wanted to virtualize, put your services into a virtual machine. And I'm asking myself, how do you ensure that your data you are using for this testing are realistic?
Can you repeat the question?
So I think there was one side where we said you want to ensure that your services are tested under realistic circumstances. So how do you ensure that your data that you're using for your engineering are realistic in its purpose?
So that depends on the service owner, how they want to do the test. So we do unit tests, right? Those are run hermetically, so we have test data for that. That can be of more or less accuracy, right? And then we have integration tests that they will compose the systems, and the the system under test will be the whole thing, not the one of the components. And those depend. There are systems that they have more advanced test data. For example, there are systems that they have, like when RPCs arrive into production, they might replicate them into the test stack, right? Others they do not. Depends on the maturity as well of the service on the testing side. Right? It's not trivial to do that. Like for example, to duplicate to the system into having a test instance and a production instance. This day with Kubernetes and stuff like that, it's easy. It's cheap to do. But replicating the traffic is tricky, because you want, for example, you don't want to put personal data of customers in your test instance, for example. So you have to have some anonymization. Then you don't want to have a system for testing that is as big as the production one, right? So do you want to reduce the amount of traffic that you send? So you want to, as well, the proportion of traffic that is mutate, reads, and so on. You want to maintain it. So it's not easy. There are some systems that do that or close, and others that they don't. Depends on the.
Okay, we have time for one last question. Then, if there are no more questions, let's stop the speaker.